The analysis of circuit involving semiconductor devices begins with the use of diodes. Diodes are the most basic semiconductor devices that we are using. Let's try to analyze a circuit with a diode in it. We have to consider this basic rule. Number one will be, we have to determine the state of the diode. The diode is considered to be in forward bias if the anode is connected to the positive of the supply and the cathode is connected to the negative. Another is, it can only be considered forward bias if the supply is greater than the knee voltage. Rule number 2, after we determine the condition of the diode, would be to redraw the circuit. So let's try now to apply the basic rules that we have considered a while ago. Consider this circuit. We have the supply, a resistor, and a diode. Consider this diode to be silicon, germanium, and gallium arsenide. Is it already in forward bias? Let us try now to solve the current that is flowing into the circuit. Let's say that our resistor is only equivalent to 100 ohms and our supply is equal to 6 volts. So how are we going to analyze the circuit? Since rule number 1 is already considered, we have now to go to rule number 2. We have to redraw the circuit. This is now the equivalent circuit of our silicon, which is in forward bias. With it, we could easily compute now the current I. Using Kirchhoff's voltage law, negative 6 volts plus I multiplied by 100 ohms plus 0.7 volts is equal to 0. I therefore will be equal to 6 minus 0.7 volts over 100 ohms. And the value is only equal to 53 milliampere. How about if this diode now is reverse? The anode is now connected to negative and the cathode is connected to positive. Letter A is no longer met. Therefore, the diode is considered to be reverse bias. If it is in reverse bias, this will be considered to be an open switch. Since it is an open switch, we could immediately say that the current is equal to 0. How important is this analysis? Let me give you another example. Let's try to consider this circuit. This circuit is what we usually see in test instruments to determine the polarity of a certain point in a circuit. It uses light-emitting diodes and considering these parameters, our test point is now connected to positive 8 volts. Considering that the anode of the red LED is connected to the positive of the supply and its cathode is connected to ground or negative, and since it's 8 volts and this one requires only 1.8 volts, then we can say that the red LED is in forward. Let's try to analyze the green LED. Its cathode is connected to positive, while its anode is connected to ground or negative. Therefore, the green LED is in reverse bias. With that, we can redraw the circuit. This is our test point now, and we have positive 8 volts connected to our resistor R. Then we have the red LED is in forward bias. Since it is in forward bias, it will be represented by a cross switch with knee voltage of 1.8 volts. Whereas the green LED is in reverse bias condition, so it is considered to be open. So that is now our equivalent circuit. Since the required current that will pass to our LED is equal to 20 milliampere, and this is but a simple series circuit, then the resistance will be 8 volts minus 1.8 volts over 20 milliampere. So this is now negative 8, and the anode of the red LED is connected to negative, and the cathode is connected to ground, which is now positive. Then the red LED this time is reverse bias. How about the green LED? Its cathode now is connected to negative, and its anode is connected to ground, where ground now is positive. Therefore, it is now the green LED that is in forward bias. With that, this will also change. Instead of the red LED being in forward bias, it's now the green LED, and this is now reverse. This is now negative 8 volts, and this is now positive. And the red LED is now open, whereas it is now the green LED that is in forward bias with a potential voltage of 2.2 volts. With that resistance, what now will be the current that is flowing in our LED? The current, therefore, will be equal to 8 minus 2.2 volts over, which give us 18.7 milliampere. When the red LED is in forward bias and the green LED is in reverse bias, when it is the green LED that is in forward bias and the red LED is in reverse bias, if, however, the green LED is replaced by a blue LED, this will pose a big problem now. Why? As an aid on the problem I have given you a while ago as an assignment, let's try to consider this circuit. Let's try to find the voltage across the resistor, and let's try to analyze the state of the two diodes. The LED will not turn on. While it's true that we followed both A and B of rule number 1, there is, however, a problem being violated. There is no way that the yellow LED will turn on simply because the silicon reaches first 0.7 volts and it remains to be at 0.7 volts. And since they are in parallel, there is no way that the yellow LED will reach 2.1 volt. With that, so our current will only pass through this path, and the current here will be equal to 0. Using Kirchhoff's voltage law, VR therefore will be equal to 12 minus 0.7 volts, which give us only 11.3 volts. If the silicon diode is not present on the circuit, using the same circuit, we know that the yellow LED will be in forward bias. However, if this 12 volts will suddenly reverse, that will pose a very big problem. Why? To avoid that, we put a silicon diode in reverse bias so that at reverse bias, the voltage across your LED will only be 0.7 and it will not reach 3 volts reverse potential. Therefore, it will not be busted. The silicon now serves as a protective circuit for the LED. That's how important a silicon is when it is connected to an LED. Do remember this problem in the analysis of the problem I have given you as an assignment.